This is the midterm project demonstration of the Multi-Purpose Device Controller by Senior Design Group 36, showcasing our innovative solutions designed to streamline and enhance the control of various platforms within a single device. Our members consist of Kenny Dow, who's a computer engineer, Johnny Blanc, who's also a computer engineer, Jason Jean Lewis, who's also a computer engineer, and Mohammed Talib Ahmed Rashid Al Fahadi, who's an electrical engineer. Our demo consists of two parts. The first part is the overall functionality of our device. The second part covers the key engineering specifications. The basic design of our device will resemble that of a modern gaming controller with action buttons and directional buttons, two analog sticks, a speaker, lighting effects using LEDs, and a battery for power. To make our device more efficient, we decided to add some advanced features to our design, including polling with the bouncing and dead zone tolerance to increase the user's input accuracy. And we also added some Hall effect joysticks for longer lasting joystick option and to decrease stick drift.
So we chose ESP32 for our PCB design because it has a certain set of features that we need for our gaming controller. First of all, the Bluetooth connectivity. The ESP32 has a built-in Bluetooth, which is gonna enable us to connect to other devices, and that's important for our gaming controller. Moreover, ESP32 has a dual core processor. This processor is able to handle up to 240 megahertz. This feature will enable us to handle big data streams. Finally, we have general input and output pins. These pins on the ESP32 will enable us to handle different protocols for our gaming controller. For our PCB input layout, making a good gaming controller is all about putting its parts on the right spots. That's really important to make sure that players having a good time using it. And the main thing is to have the buttons and joysticks on the right spots because they're effective, how comfortable the controller will feel on the user's hands. And for playing for a long time, we want to avoid making the user's hand tired and keep the grip feeling easy and natural to make the playing games fun.
Our device will connect to the platform device via a Bluetooth Low Energy protocol or a wired connection via USB.
The integrated speaker in our gaming controller is designed to enhance the experience of the user. We've taken power consumption into consideration. That's why we're using the speaker only to give cues to some important things like device connectivity and battery mode. We have decided to include RGB LEDs in our design, and it has three basic jobs in our charging circuit. The first LED is to indicate if there's any power flowing to the battery, and that's gonna be yellow for the charging status. And then if the battery is charging, it's gonna be red, and that's the charging status. And if it's full, that's gonna be the green LED, which means the battery is done charging. To power our PCB design, we're using a lithium polymer cell. The serial number for it is 653042. The battery is providing around 820 milliamps per hour, and our PCB is using around 150 to 250 milliamps in best case scenarios, that which allows us of at least 5 hours of usage time for the battery.
Button debouncing enhances the user experience by providing reliable and predictable responses to input actions. Without debouncing, users may experience erratic behavior when interacting with buttons. Overall, dead zones play a crucial role in our design by providing a buffer around the sensor position of the analog sticks. Small movements are disregarded to prevent unwanted actions and enhance control precision. This contributes to a smoother and more responsive control and improves the gaming experience, allowing players to fully immerse themselves in the game without frustration caused by unintended movements and inaccuracies in control input.
For the joysticks, we picked Hall effect joysticks, and it offers advantages that is highlighted in the magnetic field-based and the contactless design. This is not only ensuring that there's an increased durability and longevity of the joysticks, but also it eliminates the issues of friction and mechanical wear. The absence of physical contact in Hall effect joysticks translate to a more stable and reliable gaming controller, and it also reduces the likelihood of input drift.
In this video, we showcase our prototype in action. The microcontroller unit is connected to a smartphone. We are able to use it as a controller. The analog stick for steering, the buttons for acceleration, handbrake, and also nitrous potentially.
Part 2. Key engineering specifications. The engineering specifications we will be demonstrating today is latency, Bluetooth range, and the joysticks. Latency Latency is how much time it takes for one system to communicate to another. A general estimate is that the average input latency for a wired controller is around 4 milliseconds, while for a wireless controller it is around 8 milliseconds. It's important to recognize that these values may vary depending on your specific setup and environment, like how close the controller is to the console or if there's anything in the way interfering. Gamepad LA is a free open source tool that you can use to measure the polling rate or latency of your gamepad, especially on PC. The program instructs the user to move the analog stick continuously in a circular motion. Gamepad LA records the time it takes for the controller to report these changes, and measures the delay between movements of the analog stick on the gamepad. The program analyzes the recorded data and presents you with the minimum, average, and max latency of your controller along with jitter. The screenshot on the top left is a test run of Gamepad LA. The tool successfully detected that our gamepad was connected to the PC. We chose option 3, which runs the test for 6,000 cycles. The results show the minimal latency, average latency, maximum latency, and jitter. Jitter is the variation in latency readings throughout the test. A lower jitter value indicates more consistent performance. The graph below has the probability in percentage on the y-axis and the latency in milliseconds on the x-axis. This is the ideal scenario where the delay between the movements and the PC recognizing it is minimal. A higher percentage on the left where the latency is low indicates a more responsive gamepad. These are the results from our 10 test runs. The average latency was 2.788 milliseconds. Although our latency appears extremely low, it's important to note that our controller was about a few inches away from the PC it was connected to. Results may vary based on distance.
So for device range, there are two different types. There's advertised range, the max range, the max theoretical range under ideal conditions, and then usable range, the practical distance you can comfortably use a controller before signal weakness. The typical living room is about 10 to 15 feet wide, and the baseline for Bluetooth range for controllers on the market is about 30 feet or 9 meters. In this video, we are showcasing our testing environment to find out our max usable range. The area outlined in blue tape is 16 feet wide, and the measuring tape is all of the additional feet that we used. This video depicts the max range we could get while still being able to receive inputs from our prototype without signal weakness interfering, and that was about 20 feet. which is the length of the blue tape area plus an additional 4 feet with the measuring tape. After running all of our tests in the same environment, the results are as follows in this table. We do have some outliers like 33 feet and 30 feet and 16 to 17, but on average, the average of all values is about 23.2 feet.
Here we are testing the joystick and implementing a dead zone. This line of code checks if the joystick reading deviates from the center position by more than the dead zone threshold. If it does, it returns the actual joystick reading. Otherwise, it returns the center position to indicate that the joystick is in a neutral position. These are the joystick readings before the dead zone. These are the joystick readings after the dead zone has been implemented. As you can see, the dead zone was able to ignore the deviated values and center the joystick position. If this was left unchecked, the controller would be unresponsive.